A single cylinder 4-stroke engine is fitted with a rope brake. The diameter of the brake wheel is 500 mm and rope diameter is 25 mm. The dead load on the brake is 200 Newton and the spring balance is 20 Newton. If the engine runs at 400 rpm, what will be the brake power of the engine? And the options are 1 kilowatt, 1.52 kilowatt, 1.98 kilowatt, 2.14 kilowatt. First consider the given data, that is dead load weight is equal to 200 Newton and spring balance reads S is equal to, let us say, 20 Newtons, and the net load W minus S is equal to 200 minus 20, which gives 180 Newtons, and engine runs at 400 rpm. Diameter of the brake drum is 500 mm. Let us say it is equal to 0.5 meters, and diameter of the rope is 25 mm and is equal to 0.025 meters. So this is the given data. So by using this method, the brake power of the engine is given by W minus S into pi into dV plus D into N by, let's say, 60,000 to get in kilowatts. So here 180 into pi into 0.5 plus 0.025 into 400 rpm by 60,000, which gives a value of 1.98 in kilowatts. So here the answer is 1.98 kilowatts, and in the option, right option is C. C is the right answer. A domestic refrigerator is working between the temperature limits of minus 30 degrees centigrade and 20 degrees centigrade. The work output of a heat engine which is working between 200 degrees centigrade and 20 degrees centigrade is used to run the refrigerator. Determine the ratio of heat transferred from the 200 degrees centigrade reservoir to the heat transferred from minus 30 degrees centigrade reservoir. The options are 0.25, 0.31, 0.42 and 0.54. First, consider a heat engine which is operating between the limits of 200 degrees centigrade and 20 degrees centigrade. Let us say first one is here T1, which is operating at 473 Kelvin. This is a 473 Kelvin reservoir, and heat rejected to the reservoir of 20 degrees centigrade, that is 393 Kelvin. Let us say this is T2. Okay, and the work output from the heat engine is used to run a refrigerator, so which is operating between minus 30 degrees centigrade, that means 243 Kelvin. Let us say this is T3, and rejected to a reservoir of 20 degrees centigrade, that is 293 Kelvin. Sorry, 293 Kelvin. Let us say this is T4. Sorry, here T2 is 293 Kelvin. Okay, let us say heat transferred from the reservoir T1 is Q1 and heat rejected to the reservoir T2 is Q2, and heat transferred from the reservoir T3 is Q3, and here heat rejected to the reservoir 293 Kelvin is Q4. Here you want the ratio of heat transferred from the reservoir to heat transferred from the refrigerator, so which gives Q1 by Q3. But here the efficiency of heat engine is given by 1 minus T2 by T1, and which is equal to 1 minus Q2 by Q1. Okay, and which is equal to 1 minus 293 by 473 is equal to here work output by Q1. So which gives the relation between the work output and heat transfer from the reservoir T1 is equal to 0.38 Q1. So now consider the COP of refrigerator, so which is given by T3 by T4 minus T3, so which is equal to 243 by 293 minus 243 and is equal to 4.86. So but the COP of the refrigerator is the ratio of refrigerating effect to the work input. Here the heat engine work output is used to run the refrigerator, so that the output, the work output from the heat engine is used as the work input to the refrigerator. So that here we got the COP of the refrigerator is 4.86, and from this equation we can write it as it is equal to, sorry, refrigerant effect to the net input of the network input to the refrigerator. So from this, but here refrigerant effect is equal to Q3, because here heat is absorbed from the reservoir 243 Kelvin is nothing but the refrigerant effect, so that is equal to Q3. So that here Q3 is equal to 4.86 times W. So from this equation we get here Q3 is equal to 4.86 times W. So but we know that the relation between the W and Q1, which is equal to 0.38 Q1. So from these two relations we get here Q3 by Q1 is equal to 1.84, but we need here Q1 by Q3, and which is equal to 0.54. So here the right answer is 0.54, and in the options the right answer is D. D is the right answer.